series of lectures on numerical optimization. So, in the last class we started discussing about unconstrained optimization, and in particular we looked at the necessary and sufficient conditions for the existence of a local minimum for an unconstrained optimization problem. So, we saw that the second order necessary conditions for an unconstrained local minimum are that the gradient at a particular point should vanish and the Hessian should be positive semi-definite. So, these are necessary conditions, and the second order sufficient conditions are that if at a particular point x star the gradient of the function vanishes and the Hessian at that x star is positive definite, then x star is a strict local minimum. And then we started looking at the algorithm for a unconstrained minimization problem. So, this was a conceptual algorithm for solving a minimization problem where we are trying to minimize the function f of x. So, the first step of the algorithm is to initialize x 0. So, initialize to some point in the space of real numbers and set the iteration count to 0, and then while some stopping condition is not satisfied at x k, one finds a point x k plus 1 such that the value of the function at the new point is less than the value of the function at the old point. After having found the new point x k plus 1, we just increment the iteration counter and check whether the stopping condition is satisfied at that point, new point, and the procedure is repeated till some stopping condition is satisfied at x k. And what we expect to get is a point x star, which is nothing but the x k at the end of the last iteration, and that x star is expected to be a local minimum of f of x. Okay, now there are different questions that we would like to answer related to this conceptual algorithm. Now, one of the first and the most important points is that how to find x k plus 1, so that the value of the function at that x k plus 1 is less than the value of the function at the current point x k. So, this is a very important question, and many optimization methods use different strategies to find out this x k plus 1. Now, the next point is that what is the stopping condition for a given algorithm. Again, there exist different stopping conditions, we will see them in today's class, and those stopping conditions are typically derived from the necessary and sufficient conditions that we studied in the last class. Now, another important question that needs to be answered is that does the algorithm converge, under what conditions will it converge, and how fast will it converge, if at all it converges. So, the speed of the algorithm in terms of the number of iterations or the input dimension, these also sometimes play a important role in deciding the speed of the convergence. Now, one of the parameters that we used here is the initialization to some point x naught. Now, does the convergence and the speed of convergence depend on x naught, the initial point? So, we will answer some of these questions in today's class, and then the remaining questions in the next few classes. Okay. Now, as we saw in the last class, the necessary second order necessary conditions for the existence of a local minimum are that the norm of the gradient at x k should be 0, and the Hessian at x k should be positive semi-definite. Now, many algorithms that we are going to study do not use the second order information. So, it is many times difficult or computationally expensive to compute h of x k. So, for all practical purposes we will not use this condition, but remember that if some extra information is about the Hessian is available, one can use that. So, we will be mainly concentrating on this first condition, which is, so the gradient vector vanishes at a local minimum, essentially means that the norm of the gradient vector should be 0. Now, when we talk about the numerical implementations of some of the algorithms, it is very difficult to ensure that the norm of the gradient vector reaches exactly 0, because we always work with the finite precision arithmetic. So, instead of checking this condition exactly, it may be a good idea to make use of some approximate condition. So, we will study some practical ways of determining these stopping conditions. Now, one of the first conditions that one can think of is that norm of g of x k is less than or equal to epsilon, where epsilon is a small positive quantity that is defined by the user. So, in many algorithms we will see this kind of condition being used. Of course, the convergence will depend on what the convergence point that one gets depends upon what epsilon one uses. So, it is a function of epsilon. So, epsilon has to be carefully chosen, and typically that is a user defined parameter. Now, many times what happens is that suppose for an optimization problem, we want to find out, we want to minimize the distance between the points. Now, if the distance, suppose the distance is specified in kilometers. Now, later on it is found that the distances have to be converted to say millimeters. Then the value of the gradient would change considerably, and therefore, this condition does not take care of the scaling of the variables. So, many a times another condition that is used is norm of the gradient at x k should be less than or equal to epsilon into 1 plus absolute value of f of x k. So, this makes use of the function value, absolute function value. So, that takes care of the scaling part. Now, in many cases it is proposed to use the relative decrease in the function value as a stopping criteria. So, this is the f of x k is the current function value, and f of x k plus 1 is the new function value. So, f of x k minus f of x k plus 1 divided by the absolute value of f of x k, that should be less than or equal to epsilon. So, remember that these all epsilons need not be same, they could be different on the epsilons used in these expressions. But the important point here is that this criteria is independent of the scaling of the variables. So, one could use this criteria to stop the algorithm. Of course, in this case this epsilon is a user defined parameter, and in this course we will typically use this criteria, but we do not have to restrict ourselves to this criteria. One can use any of this criteria depending upon the requirement. Okay. Now, another important point that we have to worry about is the speed of convergence of optimization algorithm. Now, let us assume that we have an iterative optimization algorithm which generates a sequence x k, and that sequence converges to some x star. Okay. Now, we are interested in finding out how fast does the algorithm converge to x star. Okay. Now, for that purpose we need to see this definition. So, the sequence x k which converges to x star is said to converge to x star with order p if you take the ratio of norm of x k plus 1 minus x star and norm of x k minus x star to the power p, and if that is equal to beta as k tends to infinity, where beta is a finite positive constant. So, typically this beta is finite because all these quantities on the left side, typically beta is positive, all the quantities on the left side you will see that they are positive quantities, and beta is finite. So, this P is called the order of convergence and beta is called the convergence rate. So, if we have a sequence xk which converges to x star and then this relationship holds, then we can find out the order of convergence and the convergence rate. Now, so you will see that xk plus 1 minus x star, norm of this quantity is the distance between xk plus 1 and x star. So, let us assume that we use the L2 norm and xk minus x star is the distance between xk and x star. So, what we are interested in finding out is that how close does xk plus 1 go to x star compared to xk, and the order of convergence is the factor, the parameter p here. Now, asymptotically you can see that the distance between xk plus 1 and x star is beta times the distance between xk and x star to the power p. So, this happens as k increases. Now, the important point to be noted is that if the value of p is higher, then the convergence is faster. So, you can see that if p is higher, then the distance between xk plus 1 and x star reduces to 0 at a faster rate. So, that is why higher the value of p, faster is the convergence. Now, beta, as I said earlier, that is called the convergence rate. Now, let us see some examples. So, let us consider the case where p is equal to 1 and beta is in the open interval 0 to 1. Now, this is called linear convergence. So, p has to be 1 and beta has to be in the open interval 0 to 1. So, let us take some example. So, let us assume that beta is 0.1 and the distance between the initial point and next star is also 0.1, and let us see how the sequence is generated. So, let us observe the norms of xk minus x star as k goes from 0 to infinity. Now, you will see that initially the x0 minus x star, the norm of that is 0.1. So, we have that initial value. Then that, because p is 1, so this quantity gets multiplied by beta and 0.1 into 0.1 is 10 to the power minus 2. So, norm of x1 minus x star is 10 to the power minus 2, and again the whole quantity is multiplied by beta and the norm of x2 minus x star becomes 10 to the power minus 3 and so on. So, you will see that in every iteration the xk minus x star, the norm of xk minus x star gets reduced by 10. So, here it was 1/10, 1 by 100, 1 by 1000, 1 by 10,000 and so on. Now, to show that this linear convergence depends a lot on this convergence rate beta, we will take a similar example. So, where we will take a value of beta to be 0.9. So, which is more close to 1 rather than close to 0. So, in the earlier case the value of beta was close to 0, now the value of beta is close to 1. So, let us keep the same initial conditions, that the norm of x0 minus x star is 0.1, and then let us observe the norms of xk minus x star. So, as is the previous case, the first x0 minus x star norm of that quantity is 1 by 10. Now, now that will be multiplied by 0.9 for the norm of x1 minus x star. So, what we get is 0.09, and then again this will be multiplied by 0.9. Remember that we are working with the case p equal to 1. So, what we get is 0.081 and 0.0729. So, now let us compare the two norms of xk minus x star that we obtained with different values of beta. So, initially they were same, but now after one iteration it was 1 by 100, while here it was 9 by 100. After two iterations it was 1 by 1000, this was 81 by 1000, and then 1 by 10,000, 729 by 10,000. So, you would realize that if beta is close to 0, then this sequence, the norm of xk minus x star, goes to 0 at a faster rate compared to the case where beta is close to 1. So, typically when we talk about linear convergence, we would prefer beta to be more close to 0 rather than close to 1. And if beta equal to 1, then you will see that there won't be a change in this particular example case, the first example. Now, let us look at p equal to 2 and beta is greater than 0. Now, when p equal to 2 and beta is greater than 0, that is called the quadratic convergence. So, let us take again some examples. So, let us take beta to be 1 and norm of x0 minus x star to be 0.1, and let us observe the sequence of norms of xk minus x star. Now, if we look at this, so initially it is 0.1 into initially it is 10 to the power minus 1, and then it moves at a rate which is shown here. So, it's now it moves at 10 to the power minus, so the norm of x1 minus x star is 10 to the power minus 2. Then remember that we have p2. So, norm of xk minus x star gets squared in determining norm of xk plus 1 minus x star, right. So, in the 3 iterations, the norm of xk minus x star has reduced to 10 to the power minus 8. Now, we can compare the 3 cases which are given here, and clearly this is the faster rate of convergence compared to this, and this is faster compared to this. So, clearly this method, the quadratic convergence gives a faster convergence provided beta is greater than 0. Now, the important point that you have to note here is that this quantity, because beta is any quantity greater than 0, so beta can be less than 1 or greater than 1. So, typically this quantity should be less than 1. So, that means that your x0 should be reasonably close to x star, so that one can achieve faster convergence. Now, there exist some algorithms where if we take the ratio of norm of xk plus 1 minus x star and xk minus x star. So, as k tends to infinity, this ratio goes to 0, and norm of xk plus 1 minus x star divided by norm of xk minus x star square, that ratio goes to infinity. Then this convergence is called superlinear convergence. So, this convergence is in between the linear and quadratic. So, many optimization algorithms that we are going to study have this superlinear convergence. So, that means that they are better than the algorithms with linear convergence, but not as good as the algorithms which have quadratic convergence. So, as we will see later that the quadratic convergence, the algorithms which follow quadratic convergence would require a lot of extra information, and that is difficult to maintain. So, that is why practically it will be preferable to use algorithms which are somewhat between linear and which have convergence between linear and quadratic, and those are the algorithms which have superlinear convergence. Now, let us see some examples. Now, let us consider the sequence with xk is equal to 1 plus a to the power k, where a is a fraction, positive fraction. Now, since a is a positive fraction, as k tends to infinity, xk tends to 1. Now, one can verify that this sequence converges linearly with the convergence rate as beta is equal to a, and this is a fraction. So, this is a linear convergence with 0 less than beta less than 1. On the other hand, if we take the sequence xk equal to a to the power 2 to the power k, where again a is a positive fraction. Now, this converges to 0 limit as k tends to infinity, xk goes to 0 quadratically with convergence rate beta to be 1. And here is the example of a superlinear convergence. One can verify that the sequence 1 plus k to the power minus k, it converges superlinearly to 1. So, these are some examples of sequences which are generated by different algorithms, where in the first case the convergence was linear, in the second case the convergence was quadratic, and in the third case the convergence of superlinear. Now, when we talked about the convergence, we use the norm of xk plus 1 minus x star and norm of xk minus x star. So, many a times it is a good idea to use error functions. So, let us see what are those error functions. So, suppose we have a convergent sequence xk which converges to x star. So, let a be some function, real valued function which is continuous. So, instead of observing the behavior of xk to x star, many times it may be a good idea to observe the behavior of exk to ex star. So, convergence properties of xk can also be studied by analyzing the convergence of exk to ex star. Now, one would wonder that if one uses different types of error functions, will the convergence behavior be different? So, in general, the order of convergence of a sequence is insensitive to the choice of error functions. So, this is not a this statement does not hold always, but in general it holds. So, let us not worry about the exceptions at this moment and take this result in a general form, where the order of convergence of a sequence does not depend on the choice of the error function. Okay. Now, with this background, now let us revisit our conceptual optimization algorithm. Now, remember that we are not going to use the second order conditions, as I said earlier, and also we want to use some practical stopping condition, and one of the practical stopping condition is that the gradient of the function should be, norm of the gradient of the function should be less than or equal to epsilon. So, till that condition is satisfied, so while norm of the gradient of the function at xk is greater than epsilon, the algorithm gets executed. Now, epsilon is a new parameter that we have introduced. So, that is a typically user defined parameter. So, we have to initialize that value of epsilon, and then finally, we will end up in a situation where norm of g of xk is less than or equal to epsilon. Now, this does not guarantee that xk is a local minimum. So, output, as a output of this algorithm, we get x star to be a stationary point of f of x, and then one needs to check whether it is indeed a local minimum or not. Now, so we have answered questions related to the stopping condition and the rate of convergence of the algorithm. Now, we will worry about the step in the step 2a of this algorithm. So, the step 2a says that find xk plus 1 such that f of xk plus 1 less than f of xk. That means that find a new point xk plus 1 where the function value at that new point is less than the function value at the current point xk. Now, how does one find this? Now, it involves two steps. So, the first step is that one finds a descent direction dk for the function f at xk and take a positive step of length alpha k along that direction such that f of xk plus 1 is less than f of xk. So, suppose this is a current point xk, and suppose we find a direction dk which is a descent direction at dk. Then we take a step of length alpha k along this direction. So, this is the new point that we get, and that point is x k plus 1, and that is nothing but x k plus alpha k dk. So, recall the definition of a descent direction, that the direction dk is said to be descent direction for f at x k if there exists some delta greater than 0, such that f of x k plus alpha dk is less than f of x k for all alpha in the range 0 to delta. So, since dk is a descent direction, we are able to find some alpha k along that direction, such that f of x k plus 1 is less than f of x k, and where x k plus 1 is nothing but x k plus alpha k dk. So, these are the two steps that are necessary for this finding out x k plus 1. So, now let us look at the set of descent directions. Now, these are the contours of the given function. This is the current point x k. Now, at x k, this is the gradient vector g k. So, in this direction the function value increases. Now, dk is a descent direction. Now, what is the characteristic of a descent direction? So, we saw in the last class that if gk transpose dk is less than 0, then dk is a descent direction for f at xk. So, which means that dk should be in the open cone, which is shown by a red arc here. So, dk should lie in this open cone, and that will make an obtuse angle with gk. So, the descent direction set is a set of all directions in Rn, such that gk transpose d is less than 0, where we are using the notation gk is nothing but gk is written as g of xk. So, set of all directions d such that gk transpose d is less than 0 is shown here by a red arc, and dk can be any of these descent directions. Now, if you see this descent direction, now if you take a step along this descent direction, now if we come here at a point, then the value of the function would have increased. So, we are not interested in that. So, we are interested in the step where the value of the function decreases. So, that is a very important step. So, now we have revised our algorithm. So, earlier we had given that find x k plus 1 such that f of x k plus 1 is less than f of x k. Now, instead the first step will be to find a descent direction dk for f at x k, and this descent direction is such that gk transpose dk is less than 0. After having found a descent direction, the next step is to get alpha k which is greater than 0 along the direction dk, such that f of x k plus alpha k dk is less than f of x k, and this point is nothing but the new point x k plus 1. So, the new point is set appropriately, the iteration counter is increased by 1, and the procedure is repeated till the norm of the gradient vector is less than or equal to epsilon. Now, we know that the descent direction can be obtained by finding out the direction d such that gk transpose d is less than 0. Now, how to find out alpha k in step 2b of this algorithm, and we will discuss that now. Now, there are two ways to determine this step length. One way is called exact line search and the other one is called inexact line search. So, in exact line search, given a descent direction dk, one determines alpha k by solving another optimization problem. So, remember that we are interested in minimizing f of x k plus alpha dk, where alpha is greater than 0. So, if we are at a current point x k, this is the descent direction dk, we are interested in finding out the minimum of f of x k plus alpha dk, where alpha is greater than 0. Now, along this direction, this is dk is a descent direction. So, we can always find some alpha such that this quantity is minimized. Now, if we take the argmin of that, then what we get is alpha k plus 1. So, alpha k plus 1 is nothing but argmin alpha greater than 0 f of x k plus alpha dk. So, now let us define this quantity as a function of alpha. So, remember now that x k is fixed, dk is fixed, and alpha is a variable. So, we can simply write alpha k plus 1 is equal to argmin alpha greater than 0 phi alpha. By defining phi alpha to be f of x k plus alpha dk. So, alpha is a scalar because it is a step length. So, this is a one dimensional optimization problem. So, whenever we are given x k and dk, we have to solve a one dimensional optimization problem to get alpha k. Sorry, this is alpha k. So, we need to solve a one dimensional optimization problem in alpha to get alpha k, and then once we get alpha k, we plug in that value in this expression to get the new point x k plus 1, and clearly since we are minimizing this, f of x k plus 1 will be less than f of x k plus 0 alpha dk, which is nothing but f of x k. So, at every iteration one needs to solve a one dimensional optimization problem in alpha to get alpha k, and that is computationally expensive. So, although this approach of doing one dimensional optimization problem would give us the exact alpha k, it is a computationally expensive approach, and remember that this has to be executed at every x k given dk. So, many times this procedure needs to be adopted or the optimization problem needs to be solved completely to get the solution alpha, and in most of the cases we are not really interested in solving this problem exactly, but our main problem is to solve the minimization of f of x. So, it may not be a good idea to do this exact line search in most of the practical algorithms. So, therefore, there are different ways to do inexact line search. Now, while doing inexact line search, we find some alpha k where the function value at the new point is less than the function value at the current point, but the choice of alpha k turns out to be very crucial. So, here since we are solving the direct optimization problem, we do not have to worry about the choice of alpha k, but once we move to the inexact line search, the choice of alpha k becomes very crucial, and we will see that using some examples. So, let us consider the problem to minimize x square. This is just a one dimensional problem that we are considering, and the function would look something like this, and we know that this is going to be the minimum, and this is also a convex function. So, this minimum x equal to 0 is also a global minimum of this function. Now, suppose that we use some iterative optimization algorithm which will generate the sequence xk using some mechanism. Now, for this problem we know that the local and global minima both are at the same point x star equal to 0. Let us assume that optimization algorithm generates a sequence xk to be minus 1 to the power k into 1 plus 2 to the power minus k and dk to be minus 1 to the power k. So, remember that this is a one dimensional optimization problem. So, dk will take the value either plus 1 or minus 1. So, one either increments or decrements, one either moves on the right direction or on the left direction. So, suppose this is the sequence which is generated by an optimization algorithm. Now, let us see how this sequence will look like. So, if you look at the sequence x, so when k equal to 0, this quantity is 1 and this quantity is 2. So, at k equal to 0, x 0 is 1. In k equal to 1, this quantity is minus 1 and this is 3 by 2. So, x equal to, so x 1 equal to minus 3 by 2, then x 2 equal to 5 by 4 and x 3 equal to minus 9 by 8 and so on. Now, let us look at the corresponding function values at those x k's. So, f of x 0 is 4, we use the same function x square. So, f of x 1 is 9 by 4, then f of x 2 is 25 by 16 and so on. So, now you will see that this sequence had generated, this algorithm had generated a sequence xk such that f of xk plus 1 is less than f of xk. So, you will see that 4 is greater than 9 by 4, 9 by 4 is greater than 25 by 16 and so on. So, every time when the algorithm moves to a new point in the sequence, the function value decreases. So, this is what we were looking for, that we wanted an algorithm which will reduce the function value in every iteration. Now you will see that the sequence. So, if we just look at this sequence, limit as k tends to infinity, the second term goes to 1 and the first term keeps oscillating between minus 1 and plus 1. So, one can realize that this algorithm, although it decreases the function value in every iteration, that does not converge. It in fact oscillates between plus 1 and minus 1. So, we really cannot think of convergence to a local minimum, which is 0. The algorithm oscillates between plus 1 and minus 1. Now, let us study the behavior of that sequence. So, we started with x equal to 2 and then if you look at we started with x equal to 2, then moved to minus 3 by 2, then 5 by 4, minus 9 by 8 and so on. So, started with x equal to 2, moved to minus 3 by 2 and then so on and so forth. Now, what is the problem here? The problem here is that the decrease in function values is very small compared to the step length, especially if you see here that the step length that one takes is of the size close to 2, but the decrease in the function value is much smaller, and as k goes to infinity, the algorithm starts oscillating between plus 1 and minus 1. So, there is a very small decrease in the function value compared to the step length, and step length was quite large. So, this is the drawback with this method, and one way to fix this is to make sure that there is a sufficient decrease in the objective function value compared to the decrease at the at the case where alpha equal to 0 compared to the initial decrease in the function value. Okay. Now, let us see another example. Again, let us consider the same problem to minimize x square, and it has a local and global minimum at x star equal to 0. So, let us assume that this time the algorithm generates a sequence x k to be 1 plus 2 to the power minus k, and decay is minus 1 always, and k goes from 0 to infinity. So, the sequence generated by the algorithm is 2, 3 by 2, 5 by 4, 9 by 8 and so on, and the corresponding the function values are 4, 9 by 4, 25 by 16 and so on. Now, you will see that again the function value decreases in every iteration. So, that condition is ensured, f of x k plus 1 less than f of x k. But then what happens to the algorithm? Does it converge to the local minimum? Now, as k tends to infinity, x k converges to 1. So, unlike the previous case where the algorithm gave a sequence which oscillated between plus and minus 1, here we have a sequence which converges. But now, if you look at the point where the sequence converges, that is not same as the local minimum. So, here is a case of an algorithm which does converge, but it does not converge to a local minimum. Now, what is the problem in this case? So, let us try to answer that. So, initially we started with x0 equal to 2, which is this point, and then x1 was 3 by 2, and then 5 by 4 and 9 by 8. So, 3 by 2, 5 by 4, 9, 8. So, you will see that initially the decrease in the function value was quite large, but then the step lengths were turning out to be very small. So, step sizes were too small relative to the initial rate of decrease of the function. Now, to tackle these two problems, we need to use some extra conditions, and these conditions were developed sometime back by Armijo and Goldstein. Wolf also gave some of the conditions to ensure that there is a decrease in the sufficient decrease in the objective function, as well as the step sizes are not too small. So, we are in this figure you will see that on the x axis we have alpha, and y axis is the function phi alpha, which is nothing but f of x k plus alpha dk. So, this is that function phi alpha which is plotted here for some problem. Now, this is the tangent to this curve at alpha equal to 0. Now, if we do exact line search, we might end up in one of these local minima. Ideally, we would like to find the global minimum which is here, but we have seen that the exact line searches are computationally expensive. So, we are not interested in finding out the exact minimum of this function with respect to alpha, but instead we want to find out some alpha such that we avoid the small decrease in the function value related to the step length and the small step sizes, which were the problems in the last two examples that we saw. So, let us look at different ways to avoid this. Now, one of the conditions which was proposed sometime back by Armijo, that condition ensures that there is a sufficient decrease in the function value. So, let us see with respect to the same function phi alpha what goes on. Now, as I mentioned earlier, to ensure that there is a sufficient decrease in the function value, we have to make sure that the alpha should be chosen such that the decrease at the new alpha in the objective function value is at least some fraction times the decrease in the objective function value at alpha equal to 0. Okay. So, suppose we consider one line which is shown here as a function of alpha. So, we call it as a phi 1 of alpha. So, this line is drawn here. We still do not know what is the exact form of this phi 1 alpha, but this line is drawn here. Now, what Armijo suggested is that you choose those alphas where the function lies below this line. So, in this case, so if you look at this part of the curve that lies below this line, then this part lies above the line, this part lies below the line, and then again it lies above the line. So, according to Armijo's condition, the alpha can be chosen such that it lies in either in this range or in this range. So, this is called the acceptable range for alpha according to Armijo's condition. Now, you will see that this condition will ensure that there is a decrease, sufficient decrease in the function value. Now, more formally, suppose if we define phi 1 alpha to be f of x k plus C 1 alpha g k transpose d k. So, this is a function of alpha. So, affine function of alpha, where C 1 is a constant which is a positive fraction. So, if we define phi 1 alpha given C 1 like this, then according to Armijo's condition, the alpha k, the step length should be chosen such that the value of the function at the new point is less than or equal to phi 1 of alpha k. So, this is called Armijo's condition. So, this step is very important, that f of x k plus alpha k d k should be less than or equal to phi 1 alpha k, and that is satisfied by all alpha k's which are either in this range or in this range. So, that is why they are denoted here by acceptable step lengths according to Armijo's conditions. Now, so this ensures that, so if you look at the right hand expression for phi 1 alpha, so g k transpose d k is the rate of decrease of f in the direction d k. So, direction g k transpose d k is the directional derivative of f at x k. Now, what we are interested in is that the f of x k plus alpha k should be less than or equal to f of x k plus C 1 times g k transpose d k into alpha k. So, there should be a sufficient decrease in the objective function compared to the initial decrease which was g k transpose d k, initial rate of decrease which was g k transpose d k. Now, this condition does not ensure that the step lengths are small. So, there was a condition which was proposed by Goldstein which ensures that the step lengths are not too small. Now, the phi 1 alpha was the function which was related to Armijo's condition. Now, here we have another function phi 2 alpha, and according to Goldstein's condition, the function phi alpha should lie above this line shown by the red color. So, that means that according to Goldstein's condition, this part of the function and this part of the function are fine. So, according to Goldstein's condition, this part is acceptable and anything beyond this should be acceptable. But we are not interested in going beyond the case where the function is greater than phi 1 alpha. So, we clip the interval for alpha at this point. So, now if we combine these two conditions, Armyho's and Goldstein's condition, so then you will see that this is the acceptable interval length for Armyho's condition, and this is the acceptable interval length for Goldstein's condition. In fact, for Goldstein's condition, any alpha where the function value is greater than this phi 2 alpha should be okay. So, ideally we should be getting this interval to be going towards plus infinity, but we have clipped it because we do not want to violate the Armyho's condition. So, if we define phi 2 alpha to be a function of where phi 2 alpha is f of x k plus c 2 alpha g k transpose d k, where c 2 is a constant in the range c 1 to 1, then the Goldstein's condition say that your alpha k should be chosen such that f of x k plus alpha k d k is greater than or equal to phi 2 alpha k. So, these are the acceptable intervals according to Goldstein's condition, these are the acceptable intervals according to Armyho's condition. Now, if we combine them, then we get what are called Armyho-Goldstein's conditions for inexact line search. So, according to these conditions, we choose alpha k such that the value of the function at alpha k. So, f of x k plus alpha k d k is less than or equal to phi 1 alpha k and should be greater than or equal to phi 2 alpha k, where c 1 and c 2, where phi 1 and phi 2 are defined using the constant c 1 and c 2, which are fractions. So, c 1 is in the open interval 0 to 1 and c 2 is in the open interval c 1 to 1. Now, so if we take the intersection of the acceptable step lengths for Armyho's conditions and Goldstein's condition, so you will see that we are interested in those intervals where the function lies below the phi 1 alpha line and above the phi 2 alpha line. So, this interval and this interval, these are the acceptable step lengths which satisfy Armyho-Goldstein's condition. Now, if you look at Goldstein's condition, you will see that this local minimum was skipped by because of the Goldstein's condition, because Goldstein's condition does not allow the function to be below this line phi 2 alpha. So, the initial local minimum of this function phi alpha was missed by the Goldstein's condition. So, Wolf proposed a condition which ensures that there is a sufficient rate of decrease of function value in the given direction. So, this is the initial slope of the function phi alpha. Now, what Wolf suggested is that the desired slope of the function should be at some prescribed times the slope at the initial point. So, this could be the desired slope, which is some multiple of the initial slope, and we are interested in those intervals where the function value has slope in the function phi alpha has a slope in this desired range. So, this becomes a acceptable step length for Wolf condition, and similarly this becomes a acceptable step length for Wolf condition plus Armyho's condition. So, one can use Armyho's conditions along with Wolf condition instead of Armyho's conditions and Goldstein's conditions. So, if we use Armyho's conditions and Wolf conditions, these are the acceptable step lengths, and formally the Wolf's condition says that choose alpha k such that the derivative of the function phi at alpha k is at least c 2 times the derivative of the function at c 0 at 0, where c 2 is again a constant in the range c 1 to 1. So, once we fix the once we have the initial slope, then what we are interested in is that finding out all those alphas where the gradient of the function phi at those alphas is at least C2 times the gradient of the function at 0. So, if we multiply the initial gradient by C2 and we get the desired. So, what we are interested in is that finding out all those function points where or finding out all those alphas where the gradient of or the derivative of phi at those alphas is at least this much, the desired slope. So, once we do that, then we combine those conditions with Armyho's conditions, and what we get are called Armyho-Wolff condition. So, either one can use Armyho-Goldsteins conditions or Armyho-Wolff's conditions to do inexact line search. Now, given all this, what is the guarantee that the algorithm would converge? So, that is, if we ensure that the direction at every iteration is a descent direction and alpha k found is using inexact line search, but which ensures that Armyho-Goldstein or Armyho-Wolff conditions are satisfied, then will the algorithm converge, or are there any extra conditions which are needed? So, we will see those things in the next class. Thank you.